Good morning, everyone. Our respected organizers, session chair, dear researchers, and academicians. I'm Engineer Aditya Singh, ISTS. I've been an independent researcher, editorial review board member in 6 American international journals: IJSSMET, IJPEA, IJSTS, IJRLETM, IJSST, IJESGT, reviewer in 10 American, 5 Singaporean, and 1 Indonesian-based international journals, alumni mentor registered by Amrita University Alumni, Amrita Vishwavidyapeetham, research mentor, Academy Innova World, Kalipur, India, and ex-alumni mentor LPU. Today's the topic for this presentation is the evaluation of climate resilient infrastructure projects to encourage digital and optimization-led engineering. This is the outline for today's presentation, which will cover introduction, literature review and research gaps, methodology, global case studies, linking case studies to digital and optimization-led engineering, results and discussion, conclusion. Introduction. Background. Climate change is no longer a future uncertainty. It is an operational constraint on infrastructure systems worldwide. Floods, heat waves, cyclones, earthquakes, and sea level rise are already testing the limits of conventional civil engineering design. Historically, infrastructure was designed for strength and serviceability. Today, it must also be adaptive, predictive, and resilient. So, in this presentation, uh, real field tested climate resilient projects will be evaluated and examined how their design logic can inform the next generation of digital optimization driven engineering frameworks. Now, climate resilient infrastructure. Uh, this question comes, what is climate resilient infrastructure? So, climate resilient infrastructure integrates redundancy, where multiple layers of protection is involved, then adaptability, ability to change response, sustainability across life cycle, and real-time responsiveness. And the traditional engineering versus resilient engineering. In the case of traditional engineering, uh, it is it emphasizes on static safety factors. However, resilient engineering is dynamic system level optimization, which is needed in the current world and for our future. These principles align with digital engineering, which also includes simulation-based design, AI-assisted optimization, sensor-based monitoring, and data-driven decision systems. Literature review and research gaps. Around 50 published studies were taken into account, and for further consideration, only the publications which were published in the recent years were were taken into consideration. Now, regarding the gaps, uh, the studies in the current existing literature, uh, there are several gaps which includes the fragmentation between digital methods and real infrastructure practice. As most of the papers focus on algorithms, synthetic data sets, hypothetical infrastructure models, or the case study papers focus on engineering features, policy narratives, or descriptive project histories. But uh, the AI ML papers and case study papers really intersect meaningfully in the current literature. So there's a need of explicit mapping between field-tested resilient strategies and digital optimization engineering logic. Then another gap is the over theoretical use of artificial intelligence without validation against real projects. Most of the papers they are using simulated hazards, idealized boundary condition, controlled assumptions, uh, evaluates performance using RMSC, accuracy, loss functions. However, the missing point is that validation against real world infrastructure that has survived extreme events. Then this also creates a credibility gap between academia and practice. Then another major gap is lack of system level multi-objective resilience evaluation. The current studies evaluates resilience in isolation, structural safety, flood capacity, seismic response. However, the missing part is the integrated evaluation, which considers safety plus economics, reliability plus adaptability, engineering plus social function. Then another major gap is the weak link between climate adaptation policy and digital engineering design. As most of the papers discuss adaptation strategies, stay qualitative currently, and engineering papers focus on the technical design. They ignore policy implementation realities. So the policy talk and engineering talk are not meeting together in the current existing literature. Then there's a limited use of comparative cross-country evidence. As most of the studies, they focus on single country studies, single hazard types. But the missing part is the comparative evaluation across climate zones, economic contexts, governance models. Need of this study? Uh, Now this question comes in the mind. So first is the bridging practice and digital engineering. The reverse the usual approach. Start from the proven infrastructure projects, extract the design logic, map them onto digital and optimization frameworks. Then another need for this study is evidence-based validation of digital concepts. As the AI will solve resilience claim is not made in this study. These principles already work, but AI can formalize and scale them. Then the system level perspective on resilience, which uh, could evaluate infrastructure as technical systems, socio-economic assets, long-term adaptive mechanisms. as only a few papers are able to integrate engineering, optimization, and social function simultaneously. Then, uh, then policy relevant, practice oriented insights uh, could also be gained from this. So this study advances the literature by systematically extracting resilience logic from globally proven infrastructure projects and translating it to a conceptual foundation for digital and optimization-led engineering, thereby bridging the long-standing gap between theoretical artificial intelligence models and real-world climate resilient infrastructure practice. Now, methodology. The literature review were considered from numerous papers, and the recent ones, which were from 2020 to 25, were considered, which were focusing on digital and optimization-led engineering, particularly in the context of climate-resilient infrastructure projects. Then case study synthesis, which included countries like Netherlands, Japan, Singapore, India, as well as Bangladesh. And linking case studies to digital and optimization-led engineering was further considered in this study. Global case studies. These four global case studies are considered in this study. Uh, Mislantinkering storm surge barrier in Netherlands, Singapore's adaptive water management systems, Japan tsunami defenses and base isolated buildings, cyclone shelters in India and Bangladesh. These are covered in the next slides. Mislantinkering storm surge barrier in Netherlands. General, this storm surge barrier, it protects Rotterdam from extreme surge, extreme storm surges. Then it is designed to close only when required. Plus, it operates using real-time hydrodynamic data, and the optimization of closure thresholds balances safety and economic continuity. The figure of this um, the figure of this uh, storm surge barrier could be seen in this slide on the right hand side, uh, which has the source from the civilengineering.org. Then, regarding the digital relevance, uh, predictive simulation models, sensitive in actuation, and decision optimization under uncertainty could be done. So resilience is not equal to over design but intelligent response, so that it could be moved further. Then Singapore adaptive water management system. Uh, it is an integrated urban drainage reservoirs and green infrastructure, which is talked about globally as the ideal model. Then real-time rainfall and runoff monitoring is done, and adaptive flood control rather than fixed capacity systems were achieved. The right-hand side shows the figure of water management system in Singapore, and the digital relevance is system-level optimization, digital twins for urban hydrology, and multi-objective planning, which includes flood control plus water supply. So resilience is a network problem, not a component problem, could be said from this case study. Then Japan, the tsunami defenses and base isolation buildings. This figure on the right hand side shows uh, flood walls, tsunami defenses, which were created after massive damages from tsunami. So the tsunami walls combined with evacuation infrastructure, the base isolation reduces the seismic demand, and because Japan frequently has earthquakes, and this was needed so that the damages in the case of uh, such happenings could be reduced significantly. Then performance-based design rather than perspective codes were achieved. Digital relevance, nonlinear dynamic simulations, performance optimization, probabilistic hazard modeling could be achieved through the digital means. So resilience is achieved through control failure modes, not absolute rigidity from this case study. Then cyclone shelters in India and Bangladesh. They are multi-purpose shelters, schools, community centers. This could be seen in the figure on right hand side. They have elevated plinths and aerodynamic roofs, which could be seen in this figure. Then the cost is optimized, yet high social impact is present. The digital relevance is optimization under budget constraints, modular design strategies, and data guided site selection. So it could be said that the resilience must be context sensitive and scalable because in these places, if the budget is high, then it won't serve the purpose uh, for cyclone shelters to be used by the locals. Then linking case studies to digital and optimization-led engineering. The present optimization logic is, although these projects were not originally designed using modern artificial intelligence frameworks, they inherently follow optimization logic, adaptive thresholds, redundant systems, scenario-based decision making. So these principles can now be formalized using machine learning, digital twins, multi-objective optimization, and real-time decision systems. So it could be said that a digital twin of a flood barrier or urban drainage network allows engineers to test thousands of climate scenarios, something which is impossible with conventional design alone. And it could also be said that the adaptive thresholds, which the optimization logic already present in real projects, there the design responds differently under different climate conditions. Redundant systems, which is already present in real projects, the backup components ensure reliability under failure, and scenario-based decision making, where the design is tested against multiple extreme events. But today's digital engineering uh, could formalize using not only a digital twins but machine learning, multi-objective optimization, and real-time decision systems. So the digital tools will not replace the engineering wisdom; they will scale and formalize it. So it could also be said that the important insights from these case studies that although they were not originally designed uh, using modern artificial intelligence or digital frameworks, they already follow strong optimization logic. This tells us something important. Good engineering has always been optimization driven, even before the language of artificial intelligence existed. And if we are talking about adaptive thresholds, in projects like Mist Lantering a storm surge barrier, the system does not behave in a binary way. It responds differently depending on sea level, storm intensity, and forecast uncertainty. This is exactly what optimization and control algorithms do. They adjust actions based on threshold conditions. Then redundant systems, in Japan's earthquake resilient buildings, base isolation systems are not single point solutions. Multiple layers of safety exist. This mirror redundancy in optimization design where systems are built to remain functional even when one component fails. Scenario based decision making. These infrastructures were designed by testing multiple disaster scenarios, floods, earthquakes, tsunamis. This is conceptually the same as scenario-based optimization used in modern computational engineering. So transition to digital engineering. Today we have tools that allow us to formalize and automate these principles. Uh, and the digital twin, uh, which is one of the important digital tools. So a digital twin will be able to work as a virtual replica of a real infrastructure system. For example, a digital twin of a flood barrier or urban drainage network allows engineers to simulate thousands of climate scenarios, sea level rise, rainfall intensity, failure combinations. Such explorations were impossible with conventional static design methods alone. So the chances will increase further with its uses. And the machine learning allows the system to learn patterns from past climate data and infrastructure performance. This enables predictive decision making rather than reactive response, which will be helpful in reducing the damages. Then multi-objective optimization, climate resilient infrastructure must balance multiple objectives, safety, cost, sustainability, and adaptability. Multi-objective optimization helps engineers identify solutions that balance these competing goals. And regarding the real-time decision systems, with sensors and real-time data infrastructure can adapt dynamically, for example, changing operational strategies during extreme weather. So the key contribution is not claiming that artificial intelligence will magically solve climate resilience. Instead, this study shows that successful real-world projects already embody optimization logic, and digital engineering now gives us the ability to scale, formalize, and improve these proven strategies to the next level for other projects to follow. Then results and discussion. The figure 5 shows the growth of climate resilient technology globally, and it could be seen that in the year 2024, around 18.54 billion US dollar was the market value of climate resilient technology, and in year 2034 it is expected to reach 92.13 billion US dollar, which is roughly five times increase in the span of 10 years. It shows that the climate resilient technology will have significant rise in the market value, and that means that demand for such technology will grow further in the future. So, investment on such technology will be a wise decision to reduce damages during disasters. Then, figure 6 shows growth of digital engineering globally. In the year 2023, the market value was 2. 2,210 billion US dollars, but by year 2027, it is expected to go 3,000 billion US dollars, which means that in the span of 4 years, it is expected to uh, increase considerably, which means that digital engineering could be invested further, and they could be incorporated in climate resilient technology. Figure 7 shows the growth of digital tools market worldwide, and in the year 2024, its market value was observed as 36.5 billion US dollars. But by 2035, it is expected to reach 100 billion US dollars. So, in the span of uh, 11 years, it is expected to go almost 3 times, which is a significant increase. And similarly, it could be said that digital tools could be invested more in the future and incorporated in the making of climate resilient infrastructure, so that the scale of the projects and improvements could be done on a large number of such infrastructure projects. Conclusion: uh, the current gaps and the relevance of this study uh, were uh, were covered, and climate resilient infrastructure, what they mean, then how resilient engineering is different from traditional engineering, which is needed for our current generation and for our future, and how digital engineering is important for climate resilient infrastructure. Then, major global case studies were considered from Japan, India, Bangladesh, Netherlands, Singapore, and how digital and optimization led engineering could be linked with such real life case infrastructure case studies, uh, particularly the climate resilient context. And the market growth and future scope uh, were examined based on the earlier graphical analysis. These are the key references. Thank you.